All right, so now that we know what polyatomics are, I'm pretty sure you're wondering, when the heck does all of this ion stuff end? Oh my goodness, Duckonta. Yes, it lasts forever. There's lots to do with ions. I mean, we've got just the ions themselves, then we've got the transition metal with ions, and then we've got polyatomic ions. So by the end of this video, you should be able to utilize, again, the steps for naming compounds containing polyatomic ions, either from the name to the formula or the formula to the name, and summarize all of the naming steps for ionic naming in general. As a side note here, have you got any sodium hypobromite? Nah, bro. If you haven't already, these are the very common polyatomic ions you should have written down somewhere, or print them out for all I care. Get them down somewhere so that you can reference them and use them every time you're naming and dealing with polyatomic ions in general. It's just a good idea. So if you're going to be naming things with polyatomic ions in them in general, the first step is that you're gonna name with the same rules as we have before. As usual, you're gonna have a metal and a nonmetal because it's an ionic bond, and the nonmetal is likely the polyatomic ion in this case. So we're going to have a cation plus the polyatomic ion's name. And where did we get those names from? Well, gee, I gave them to you here because you need to write them down. These are the names you're going to use for the polyatomic ions. So no, seriously, like pause the video here and write these down. Then step 2 would be to find the polyatomic ion from that nifty little list you wrote down and insert the name after the cation's name. The exception, and the only exception you have to worry about with this, is ammonium, because ammonium would be coming first as the polyatomic cation, and then you'd have to end it with an anion ending in "ide." You want to get in the habit of putting parentheses around your polyatomic ion to show where the cookie starts and where the cookie stops, so you have a good idea when you drop and swap that you're not dropping and swapping to inside your cookie. You want it on the outside so you know how many cookies to actually have. If you don't understand the cookie reference, please check out my polyatomic ion video, linked in the description below. So here we're given a molecular formula with a polyatomic in it, and we want to name it. First and foremost, how do I know that there's polyatomic ions even present when I look at these? Well, let's break it down. We know that Li stands for lithium, we know that N stands for nitrogen, and we know that O stands for oxygen. Thus far, we've always seen a nonmetal and a nonmetal, a metal and a nonmetal, so 1 to 1, there's 1 and 1. In this case, there are 1, 2, 3 different kinds of atoms. If there are that many different kinds of atoms present, you know that there has to be a polyatomic. And again, other than ammonium being the exception, the polyatomic is usually going to be the second one, the anion. So I would lump together the N and the O3 as our polyatomic ion. In this case, we're just going to say, oh, Li stands for lithium, so I would write out lithium. And NO3 is a polyatomic ion where I can just find the name in the chart that I wrote down. NO3 is right here. It stands for nitrate. So I would just write nitrate. And my final answer is lithium nitrate. Next is CaCN2. Notice again here we have a calcium, we have a carbon, and we have a nitrogen. That's 3 different types of atoms all together. That's a dead giveaway, red flag that we have a polyatomic ion present. And in this case, the parentheses are already there, so we know what the cookie is. We have Ca for calcium, so I'm just going to write my cation first, calcium. So we've got calcium, and then what does Cn stand for? Looking over at our chart, Cn stands for cyanide. So we're going to write cyanide. Calcium cyanide is our final answer. Not too hard, right? And then finally, we have Na, that's 1 atom type, H, hydrogen, C, carbon, and O, oxygen. We have 4 atom types in this one molecule. Definitely a polyatomic ion. Na stands for sodium, so I'm going to write sodium. And then this whole thing is a polyatomic ion. Let's look for HCO3 in our list. That stands for bicarbonate. So we're going to write sodium bicarbonate, which is more commonly known as baking soda. All right, now here is the ultimate level up and final test for ionic naming. Now we can have ionic compounds that contain both polyatomic ions and transition metals. Dun, dun, dun. Can you do it? I believe in you. Yes, you can. We'll do this together. Step 1, we're going to start naming with the same rules as we always have before. We're going to have, if there's a transition metal there, we're going to have our cation first, a Roman numeral in parentheses to indicate the charge of the transition metal, and the anion would end in "ide." Step 2 would be to find the polyatomic ion from the list that you wrote down and write its name out after the cation. And again, as a reminder, if there's more than one of them, you need to keep the polyatomic ion all together in parentheses so that you can indicate where the cookie starts and where the cookie stops. So here's step 1, step uno, for your polyatomic ion and transition metal naming scheme. Identify whether there's even a polyatomic ion to begin with. And the clue is there's many atoms together. There's more than just 2 atom types present. And you also have to recognize, is there a transition metal present? So my example for you is PbC2H3O2. Okay, there's a lot of atoms present there. There's many atoms. So right away we know, check, that is definitely a polyatomic ion that's present. Now we need to look at our cation, Pb, not peanut butter jelly, but lead. Lead is one of our transition metals. So check, we have the scenario where there's a transition metal and a polyatomic ion present. So now we have to mash together the steps that we used for transition metal naming with our polyatomic ion naming. The easiest way to do this is to separate the 2 species from each other, so the 2 different atom types, our metal and our polyatomic ion, separate away from each other to determine the charge on each. This gobbledygook of a polyatomic ion right here is called acetate, and we have 2 of those. So if you look at this, we have 2 whole cookies of acetate present for every 1 atom of lead present. That's why I drew 1, 2 cookies of acetate present. And each acetate, looking back at my polyatomic ions list, possesses a charge of -1 per cookie. So overall, I have together a charge of -2 between both acetate cookies. That means that lead itself must have a +2 charge, because +2 - 2 gives me an overall 0 neutral molecule. Now that we've determined the charge that should be on the cation, our lead, so we know that it has to be +2 charge, now we can name it with the numerals. Now we would write out the word lead for Pb, Roman numerals 2 for the charge, for the +2 charge, and acetate from our polyatomic ions list. Now, whoa, buddy, you're really gonna wanna pause the video here and try these before I show them to you. It's very important that you actually do try these and pass them through your own neural pathways to make sure you're understanding the words that are coming out of my mouth. So go ahead and pause now, please.
2 hours later.
All right, for our first example of try it questions, we have copper to hydroxide. You should first note that copper is a transition metal because it has the Roman numerals present, so I know it's got to be a transition metal. And hydroxide, that sounds like more than 1 atom, and that means it's got to be a polyatomic. So that means we're going to use these new steps we just learned. We're going to have copper, which is Cu, and we know it has a +2 charge thanks to that Roman numeral, so +2. Hydroxide from our polyatomic ions list is OH, and that whole cookie has a -1 charge. Hopefully you're seeing that 2 - 1 gives me 1 and not 0. The whole goal is to be neutral, is to be 0. So we need to do our drop and swap method here to make sure that we do have a balance in charges that equals 0. We're going to take this 2, put it on the outside of the parentheses down below, and this 1, put it down here at the base of the copper. So what we end up with is Cu1 OH2. Now, why did I put the OH in parentheses? If I didn't, it would look like this. Now, that would be an entirely different molecule. For example, for Cu, parentheses OH2 means that we have 2 OH groups, whereas the one below it, this one, CuOH subscript 2, means that we have one Cu, one O, and two H's. Those two molecules look insanely different. The first one would end up having two OH groups around it, whereas this one here would be missing an oxygen altogether. So do make sure that you are very diligent with your parentheses and containing the entire amount of atoms in your polyatomic ions. Next, we have cobalt 5 sulfate. Cobalt is CO, and it has a charge of +5, thanks to that Roman numeral telling us so. Then we have sulfate, means it ate a little bit too much. That's going to be SO4 minus 2 charge. I'm going to put that in parentheses, SO4 minus 2 charge for sulfate. Now all we got to do is our drop and swap, and we're going to take this 5 and put it on the outside of the parentheses, and take this 2 and put it at the bottom of the cobalt. Our final answer looks like this: CO2 parentheses SO4 to contain our entire polyatomic ion cookie together with a subscript of 5. There are 5 sulfate cookies for every 2 cobalts. Manganese 2 carbonate. We have Mn, and the Roman numeral tells us that it's a charge of +2, so +2 for our manganese. And carbonate, CO3, the whole cookie is -2 charged. In this case, we have it pretty easy because 2 minus 2 just gives us 0, so we just have to put those two together, MnCO3, and we're all done. Next up is tin 4 acetate. Tin is Sn, so we're going to write Sn. Thanks to that Roman numeral telling us so, we have +4 charge up there. And acetate, I endearingly refer to as CHQ, is CH3COO -1. We're going to drop and swap, take this 4, put it on the outside of acetate, our CHQ, and 1 at the bottom of our Sn for tin. What we end up with is Sn parentheses CHQ for acetate with a subscript of 4. And finally, we have lead 4 dichromate. Lead is Pb. It's peanut butter jelly time. Also has a +4, and dichromate is a polyatomic ion, which is Cr2O7 -2 charge overall. We're going to drop and swap those numerical values for the charges. We got the 4, drop it down there. The 2, drop it down there. And what we end up with is Pb2 Cr2O7 as our polyatomic ion cookie altogether, subscript 4. Now, just as before, we could reduce that down and we could say, oh, that's actually Pb Cr2O7 2. Now, I've mentioned ammonium being an exception a few times, but here it is officially. The one and only polyatomic cation is known as ammonium, NH4+1. And to name it, we're always going to have ammonium as our first cation, and then the anion is going to end in "ide" as usual. Unless, of course, ammonium happens to be paired with another polyatomic ion, then you would just use the anion's polyatomic name, and you wouldn't have to end that in "ide." So for example, if I was going to pair ammonium and nitrate together, both of which are polyatomic ions, I wouldn't convert nitrate to nitride. I would say nitrate still. So there you have it, both examples. For ammonium with a normal anion like sulfur, it would be ammonium sulfide. But again, if it was with another polyatomic, you would just keep the polyatomic's whole name, not changing anything. Ammonium nitrate as an example. Here's our last try it for this lesson. Go ahead and pause the video here and give it a shot.
2 hours later.
We've got zinc phosphate. Now, zinc is one of those transition metal exceptions in that it's not going to need a Roman numeral because it always forms the same charge, if you remember from a previous video. Zinc always forms a +2 charge. You can remember that because the Z kind of looks like a 2 in zinc. So we're going to write Zn +2. And phosphate is one of our polyatomic ions. It ends in 888, and it's right up there. PO4 -3. I'm going to put that all in parentheses, PO4 -3. I got to do my drop and swap now. I'll take this 2, put it down on the bottom, take this 3, put it down here, and my final answer ends up looking like this. zinc 3, PO4 2. Now remember, I keep those parentheses around my PO4, otherwise it would look like I have 42 oxygens. That's not possible in this one molecule. For potassium chromate, first we're going to write our potassium K, and it has a +1 charge from our periodic table. And chromate is our polyatomic ion that we're just going to pull from our list. That's CrO4 minus 2. Now after we drop and swap, we take the 2, put it down below, the 1, and put it on the outside there. We end up with a final answer that looks like this. K2CrO4 1. And now I don't need to show that 1. Again, it's implied that there's one whole cookie of chromate present. Next up is ammonium hydroxide. Ammonium is our exception for polyatomic ions, and there happens to be another polyatomic with it, hydroxide. So this is one of those ones where there's 2 polyatomic ions making 1 molecule. And if you notice right off the bat, we have a +1 charge here, a -1 charge there, meaning that 1 minus 1 gives us 0, so we don't even have to drop and swap. We can just write NH4OH, and we're done. Calcium nitrate. Calcium is Ca +2. And nitrate ends in 8, so it's a polyatomic ion right there, our NO3 minus 1. We're going to put it all in parentheses, NO3 minus 1. Now all we got to do is drop and swap. We're going to take that 2, put it at the base, take the 1, put it at the base of calcium, and our final answer looks like this. CaNO3 subscript 2 on the outside of the parenthesis. Now again, if I forgot these parentheses, that sure looks like 32 oxygens, not 2 nitrate cookies. Be diligent with your parentheses. And for our last practice, we had to throw in one where I give you the molecule and we have to figure out the name. Here, we notice that there is 1, 2, 3 types of atoms present, so we know there has to be a polyatomic ion here. The cation is Na sodium, so let's just write out the name sodium. And everything that's left over, ClO4, we should find in our polyatomic ion list. Hey, how convenient. ClO4 is right there, perchlorate. So all we have to do is write perchlorate. The final answer is sodium perchlorate. So overall, here's the summary for naming ions in general. We have 3 naming cases when it comes to ions. The first is just a normal metal with a nonmetal. That's the premise of all ionic bonding, a metal with a nonmetal. And we're always going to take the cation's name plus the anion's name ended in "ide." The second case that we can have with naming ions is that we have a transition metal with a nonmetal. In that case, we're going to take the cation transition metal, indicate its charge with a Roman numeral in parentheses, and then have the anion always ending in "ide." And thirdly, we have the option of having a normal or transition metal with a polyatomic ion. For that, you'll have to take this option plus using the polyatomic ion chart to find the name of the polyatomic ion you're looking for. Remember that a polyatomic ion is inherently composed of nonmetal atoms themselves, and the transition metal will always have the Roman numerals to represent its charge. I hope this keeps all your charges straight when it comes to ions and ionic bonding. And if you're feeling a little down today, make sure you get rid of some of those extra electrons and become a cation. Give me a quacks up and subscribe for more educational content, and see you later.
No ducks, no glory.